In deep geothermal applications, temperatures often exceed 100 degrees Celsius. Since the boiling point depends on pressure, liquids remain stable as pressure increases with depth, making multi-phase treatment unnecessary. However, the density changes become nonlinear and viscosity changes become significant. Besides the usability and meshing features, newly released FEFLOW 10 comes with multiple numerical improvements. Key among these is a pressure-dependent boiling point, implemented through a new auxiliary parameter, temperature relative to boiling. This parameter helps you identify the validity of the liquid phase and can be used as a proxy to locate regions that may require multi-phase treatment. We've also added a new equation of state. Access it via a dedicated page in the Problem Settings dialog, where you can decide whether fluid density should have a dependency on temperature and concentration. The linear dependency of fluid density on concentration works the same way as the density ratio feature in previous versions. However, FEFLOW 10 introduces the ability to control this parameter globally, rather than assigning it to individual elements. Similarly, the linear dependency of fluid density on temperature retains the functionality of the expansion coefficient from earlier versions. This parameter too can now be applied globally or on a per-element basis. The extended equation of state supports nonlinear dependency on temperature, nonlinear dependency on temperature and pressure, and nonlinear dependency on concentration, temperature, and pressure. Fluid density is now a process variable, calculated directly at local finite element nodes for greater precision. These features extend FEFLOW's applicability to scenarios involving high concentrations, up to 300 grams per liter, extreme temperatures up to 300 degrees Celsius, and high pressures up to 100 megapascals, like deep geothermal reservoirs, lithium brine deposits, and hypersaline environments. Testing these options is as simple as a single click, allowing you to evaluate their impact on FEFLOW's numerical solutions. So if you're working on extreme cases with density-driven flow where you expect formation of convection cells, we've got you covered. FEFLOW 10 introduces a new standard formulation for mass and heat transport equations. Legacy options are still available for comparison. The new default formulation builds on the former convective form with an important enhancement. Mass and heat boundary conditions of the second, third, and fourth kind now allow total flux to be prescribed by default. This implementation provides significantly more flexibility in controlling mass and heat fluxes, particularly for injection boundary conditions in projects like deep geothermal systems or return flow from direct lithium extraction. Take your numerical modeling to new heights and upgrade to FEFLOW 10 today.